So I'm going to tell you about our project, Advanced Hardwood by Biofuels Northwest. We are a consortium of university and industry partners throughout the Pacific Northwest. Glad to see that the poll is working. Thanks for that. And we are led by University of Washington. And then we have industries partners, Greenwood Resources, Zeachem are our two main industry partners, and then other Northwest universities. And the one we're going to be working with today is Portland State. What we do on this project is we do the research and development in terms of growing poplar trees more as an agricultural crop, harvesting them on very short rotations, 2 to 3 year rotations, as you can see the harvester from New Holland Agriculture on the left side of your screen. And then we take that poplar trees and we do the research into turning them into sustainable transportation fuels and also biochemicals. This project is funded by the USDA National Institute of Food and Agriculture, and this is the 5th year of a 5-year research project. I'm now going to be turning this over to our presenter for today, and he is Dr. Todd Rosenstiel. He's from Portland State University, the Department of Biology, and he is going to be speaking to us about bioenergy crops and how they will be affecting regional air quality. Most of his work is going to be focused on poplar, but he's also going to be giving examples from other bioenergy crops as well. So, and you should be able to type in questions in the chat window, and then Todd will be available at the end of the webinar today to answer them. So I'm going to turn the mic over to Todd now.
Okay, good morning, everyone. My name is Todd Rosenstiel. Hopefully you can hear me. It seems I'm broadcasting live from downtown Portland as we speak. So I'm a professor of biology at Portland State, and I'm also part of what we have a climate and aerosol research group. And Patricia and folks at the Advanced Hardwood Biofuel Project asked me to do a brief webinar to bring you up to speed on some of the work that we're involved in. And I think in the bioenergy industry in general, it's important to know a little bit about aspects of environmental sustainability and to really sort of be as up to date as possible on some of these issues. I have a background as a tree physiologist, in case you're wondering. I've probably spent 20 years working on some aspect of poplar physiology or poplar biology. But about half of my lab works on some aspect of air quality, and mostly we work in mosses of all things. So if you've heard much about Portland and moss stories and pollutants and toxins, that stuff we're deep involved in, but I have a long interest in air quality. So with that, I've kept this pretty short today. We've only got about 20, 22 slides, so I want to leave plenty of time for chat questions, and I'm happy to take those questions at the end. Also, I just want to state right up front, if at any point, after this talk, I put my email here, please contact me if you have specific questions or if I can help you think through some of these issues, or if you're just looking for more information. I'm totally happy to answer any questions of folks who've signed up this morning for the webinar. Okay. All right. With that, we'll kind of move right on. So, a little bit about what we do know. What do we know? And this is not a surprise to anyone, hopefully. If any of you take a nice walk in a Doug fir forest this weekend or last weekend, you can kind of smell the landscape that you're in. It should come as no surprise that plants emit volatile organic compounds. And I'm going to refer to those as VOCs moving forward. On Valentine's Day or sort of Mother's Day, we were all deep in giving flowers, and what we love about flowers is basically the VOCs they produce. My lab's very good at quantifying, measuring all the different chemistries that are coming out of plants, and mostly when we think of plants and VOCs, we think of flowers. But I think it's important to realize that plants and ecosystems release all sorts of other VOCs from other structures, and we're particularly interested in the compounds that are emitted from plant leaves. So you don't have to have flowers to emit scents, and in fact, I think that many of you who've worked in the agriculture industry, you can often, if you were to close your eyes, you might actually be able to smell what type of field you're in. And this is an area that my lab has worked on for many years. Okay. Oh, and I should say, actually, looking at the screen, one more area. One of the primary groups of compounds. Many of you are used to a solvent, turpentine. So turpentine, of course, is a liquid solvent derived from natural plant products, and it's really made up of these terpenoid and sort of sesquiterpene type compounds. that we're all familiar with. We'll be talking a fair bit about the molecule today called isoprene, which it looks like in my screen didn't quite resolve, but isoprene's really just a little 5-carbon volatile molecule. You can't really smell it unless it's in really high concentrations. But for some of you who may know something about chemistry, isoprene is the backbone for all natural rubber and latex. So if you're going to make a natural latex or rubber compound, you're actually going to do it by building from the backbone of this 5-carbon isoprene molecule. So we got a few more problems here. So although it should become no surprise that plants emit volatile scents and we can smell them, I think what is often of surprise to people is the magnitude at which plants release these compounds to the atmosphere. So here's just a little table put together. Again, it looks like there's a little, my apologies for some unclarity in those symbols, but on the left is a listing of different volatile compounds, methane, which many of you may be familiar with, and then these other compounds, isoprene, monoterpene, ethylene. You know, methane generally people would recognize as a really significant amount of organic carbon that's loaded to the Earth's atmosphere. And when we look globally, it's probably the single largest organic molecule that the biology of Earth pumps up into the atmosphere. And we all know it's important for global warming, global change, because it's a long-lived atmospheric molecule. But what most people may not realize is that methane is actually pretty much trumped if you were to start to add up all of the other plant-derived VOCs. And so that fourth column there gives you the annual global emission. And for many of you, these numbers won't mean much. This is in teragrams of carbon. But to give you an idea, 1 teragram of carbon is basically 1 million tons. So, you know, an isoprene, that second column, we're looking at a billion to maybe 5 billion tons of isoprene that are emitted to the Earth's atmosphere every year by plants. So this is a really sort of significant and large number. The question is, what does that mean, and why does that have any relevance to bioenergy, which is where we're heading next? Well, so many of you, if you've, I'm here in the Northwest, but I did not grow up in the Northwest. I spent most of my time in farm fields in the Midwest, but have traveled a lot, including here to the Great Smoky Mountains. And many of you may have also been to the Great Smoky Mountains and wondered basically, where that blue haze comes from. I put this slide up to remind ourselves that natural ecosystems have a really amazing property to sort of engineer the atmosphere. And so here in the Great Smoky Mountains, well before there's any industrial revolution or even really much human sort of advanced development present, these regions were always known for their blue haze. And we've now come to appreciate that that blue haze is really a consequence of these specific VOCs and other particles that are moving up into the atmosphere and actually directly sort of affecting the refraction of water. So an interesting sort of area. So where that blue haze comes from. So what else do we know? So we know that plants make VOCs. We know that plants release an awful lot of VOCs when you look at the whole planetary scale, and that those plant VOCs can impact atmospheric chemistry. So I'm not going to go too deep into the weeds in the atmospheric chemistry, but I think it's just important to understand this topic, so at least at some base level. So realize that any VOC that's emitted to the Earth's atmosphere must eventually come back to the surface, right? If we're emitting tens of millions or hundreds of millions of tons of VOCs to the atmosphere every year, somehow that has to come back. And the way that comes back is mostly through the little scrubbing bubbles of the atmosphere called hydroxy radicals. These are the OH radicals that convert the VOCs back to carbon dioxide or carbon monoxide or some other product. And eventually those carbon molecules either rain back on Earth's surface or they're retaken up in the form of carbon dioxide so the trees can grow some more. So, we're working in a closed system, so everything that goes up to the atmosphere must eventually get cycled back. So what's really unique about plant VOCs, and there's a picture of what the isoprene molecule looks like, these molecules don't last very long in the atmosphere. They're considered to be very highly reactive, which means if there's a little bit of OH radical or there's a little bit of nitrogen oxides around, those molecules are quickly basically oxidized and converted to other things. Now, under some conditions, if plant-derived isoprene is released into an atmosphere that has a lot of NOx, that's the top arrow right here, and I think my pointer works, hopefully. The top arrow here, you can actually, believe it or not, lead to the formation of tropospheric ozone. So there are certainly conditions by which isoprene in the presence of NOx can lead to the formation of ozone. We also now know that isoprene, as well as other plant VOCs, can directly oxidize and make little aerosol particles. And aerosol particles are basically, small particles of organic molecules surrounded in water, and that's essentially what's leading to the haze that you would see over the Smoky Mountains or even some regional urban hazes. Right? The other possibility is that these reactive compounds, because they're so reactive, they get really attacked by the hydroxy radical. And these hydroxy radicals are really the little scrubbing bubbles of the atmosphere. And these little scrubbing bubbles would rather be spending their time doing things like scrubbing out methane, which helps us with respect to global warming. But if there's a lot of VOCs around, there's only so much OH. And so essentially that OH, instead of attacking methane, attacks the VOCs. And actually there can be this weird sort of feed forward process with respect to VOCs and global warming. And if you want to hear anything more about these sorts of issues, I had the weird opportunity to be interviewed by Ira Flato a few years ago on Science Friday, and that was an interesting trip to sort of talk about at the national scale these issues of trees and air pollution. Okay, so a little background. We know plants make VOCs, we know plants make a lot of VOCs, and we know that certain VOCs can impact atmospheric chemistry. What does this mean for bioenergy? And again, and this is, I always hate to sort of sit here in the current climate and suggest that even back from the 1980s, Ronald Reagan was correct. But certainly in many cases he was, in suggesting that there are cases under which emissions from, say, automobiles or industry and NOx, and plus VOCs from all sorts of trees in biology, and I'm focusing on trees, but trees aren't the only sort of bioenergy crop that are making VOCs, or any could actually lead to the formation of ozone. Okay, but yeah. Give you some concrete examples. I think oftentimes when people first hear about this, they may think, oh, this is ridiculous. Trees really pollute? And I'm like, well, yes and no. And so it's a slippery slope. And essentially we have to always think about where we're located and what scale we're talking about. And that's what's going to be the issue of today's talk. So I don't want you to take away a message thinking that I believe trees are polluting and we should cut them all down. I certainly do not. But this is an issue that at least we need to be aware of. Particularly I'm sensitive to this because living in a very urbanized area, we live in very engineered landscapes. And so as we start to think about where we're going to site various, say, plantations or site various industries, this is just an area that we need to be aware of. Okay, but what are some concrete examples? So I'll give you an example here from the tropics, oil palm. So in the bioenergy industry, oil palm is probably one of the golden childs in terms of, monetary return for sort of acre planted. So much so that, back in 1974, only less than 1% of all of Borneo was covered in oil palm. And now we're 13, and I think the latest numbers are 16 or 17%. Some of you may know better than I, in terms of total land area of Borneo covered by oil palm. Now, oil palm is an interesting species because it is also a very significant emitter of isoprene. And that top graph here basically shows you some very interesting results. So in the oil palm world, mostly what's happening is you're replacing and taking you're taking more pristine, I wouldn't say pristine, you're taking traditional rainforest systems or intact rainforest systems, cutting them down, planting in oil palm, and that's leading to all sorts of environmental issues. But one issue that hasn't received much attention is what happens to the atmosphere when you do that. And here's just a graph showing how much isoprene is emitted on a daily time course. You notice as the sun comes up comes isoprene, eventually the sun goes down. So these things are linked to basically photosynthesis and linked to sort of daylight cycles. And you can see what the isoprene emission would be from an intact rainforest. And then this is what the isoprene emission is from an actual intact oil palm plantation. And so literally you could have something of almost 6 to 7 fold more isoprene emission from these oil palm plantations than you would have from the rainforest. What does that fundamentally mean? Well, thankfully, currently at least, in Borneo, if you've been to Borneo, it's not a particularly industrialized area, which with respect to air quality is a good thing. It means this landscape can actually absorb this increased emitted isoprene with relatively little impact on atmospheric processes. However, if Borneo continues to develop at the rate it's currently developing, and we were to increase the amount of background nitrogen oxides, such as maybe you would find in the rural United States, then what happens is you start to spit out massive amounts of ozone simply as a consequence of these oil palm plantations. Now, this is a very unique sort of circumstance, but it lays the context by which this is not an area that we want to necessarily ignore. In fact, just something we need to think about going forward as we plan planting. Another local example, which is more local, meaning domestic in the United States, would be what we understand about kudzu. And many of you, if you've spent any time at all in the southeast United States, you know very carefully not to park your car anywhere near a kudzu field because you may come back the next afternoon and it will be buried. Kudzu is an interesting, incredibly invasive species. That has the amazing power to not only manipulate, the terrestrial ecosystem, but is also really manipulating the atmosphere. And it does that both through the primary emissions of isoprene, as well as because it's a nitrogen fixer, it actually kickstarts NOx emissions out of soil. And what's kind of fascinating to me, at least, is that it's the combination of those two things, increased nitrogen oxide emissions plus the increased VOC emissions, that this group a few years ago in the Proceedings of the National Academy of Sciences was able to model and show just the invasion of kudzu alone was leading to, at least in this case, a scale of number of days that this region would be out of ozone attainment by the 8-hour EPA standard. And essentially what you're finding is that just the presence of kudzu alone could cause you to be out of air quality attainment anywhere to 3 to 7 days a year. So point being, plants absolutely do have an impact on atmospheric chemistry and atmospheric quality. And when we start to connect the dots between air pollution and human health and air pollution and various ecosystem services, this is just simply something that needs to be put in the equation, but really I would say until very recently hasn't received much attention. Okay. A little background, and I'm happy to share any of those references later if you would like. Well, where does this bring us to bioenergy? Well, I find this a particularly interesting thing because as I tell my students, we're kind of in the middle of the next green revolution, which is we're almost overnight changing some of our domestic cropping systems. Now, unlike traditional ag crops, many of the emerging bioenergy crops we all know and love can and do emit significant quantities of VOCs. Now, this is a very different landscape than we've been in more traditional cropping systems where we've had, let's say, hundreds of years or multiple centuries of selective breeding for agricultural crops. Oftentimes, from a plant breeding perspective, you're trying to keep the carbon economy as tight in those crops as possible. You don't want any carbon to leak out of the system because you want to have a bigger corn cob or you want to have a better fill in soybean or something like that. We haven't really had the luxury in our bioenergy crops to have the breeding background and the history to basically tighten up their carbon economies. And as a consequence, we see these crops, and I make a list: eucalypt, acacia, poplar, willow, oil palm, rubberwood, arundo, bamboo. These are sort of global crops that actually do emit significant quantities of VOCs. And so this, I got interested way back when I was a PhD student, just because I found this a super interesting area to understand how large-scale land use change may couple to atmospheric properties. Okay. Okay. Now, I should also make a point there that although these all emit different quantities of VOCs, they also emit very different complements. So not all species are the same with respect to what compounds. Many of you might recognize the scent of eucalyptus if you were to crush it. And you just know from practice, if you crush a eucalyptus leaf in your hand and smell it, it does not smell the same as crushing a poplar leaf in your hand and smelling it. And so that different scent is, of course, the different complement of compounds. And each of these different compounds can spin out in different ways and influence atmospheric chemistry. That's something right. Okay, very good. Okay, so what are we up to and what are we doing these days, and how might we be able to give you a little assistance in thinking about how to apply some of these principles to air quality to management of bioenergy systems in the United States? So I'm just going to give you a few little snapshot of 3 things we're working on, and I just want to right up front say that this is an area that folks have been working on for quite a while. However, I think as we're moving into new ways to cultivate crops and new different levels of scale, I think we're trying to develop some new techniques that can be particularly useful. And my interest is, to fundamentally support the growth and development of the bioenergy economy and trying to find ways that we make sure we're attentive to aspects of environmental sustainability and that we get ahead of any issues if we think they may be a problem. All right, so what are we trying to do? A few things we work on is, of course, modeling. So we do some atmospheric chemistry modeling, and that's really important. I'll just give you a little background on what we're doing. I'll talk about ways in which we're trying to screen plants for VOC emissions and what we're trying to do at the field scale, and then make some general recommendations. And again, my point of this particular webinar is mostly to give you some information so you're up to speed, so that if you are a grower or you're a developer or bioenergy, particularly of poplar, that you're at least aware of this particular issue. I think to cut to the chase, I'll give you some evidence that in the Pacific Northwest, I think it's not of great particular concern unless we get to really large scale plantations, and we can talk about that. But in general, this is more an issue that I think it's important to understand. So let's do a little of the modeling. All right. So this is important because if you're going to understand air quality is a world that is all about modeling space. And I'm not going to dive into the weeds in terms of what we're doing, other than to give you some background, because I'm about to show you some slides that might be useful. How do you, if you were to ask what impact do bioenergy crops have on a landscape scale, one way to do it is to basically work in this modeling space. And by this, it really is a model that we use, which would be called WRF-Chem, which is a weather research forecast chemistry model. This big, very complicated model spits out all sorts of information, such as how much ozone do you have, how many aerosol particles, but you have to feed it other sort of landscape level information. So we've worked out a flow path to do that, where we can basically say, okay, how much bioenergy crop at what scale, how much emissions do those crops have. So once we know something about the magnitude of the scale, you're going to plant, let's say, 1,000 acres, or you're going to plant 10,000 acres. Where are you going to plant that? What is the growing condition like? Which species? We can take those emissions, feed them into this WRF-Chem model. At the same time, we need to know something about where are you planting those trees. That's very important. And I think in this world of atmospheric chemistry, much like crops in general, scale and context is totally important. Which region are you planting in, and what is the background atmospheric conditions like in the region you're planting in? Luckily, we live in the Pacific Northwest, which is incredibly clean relative to other parts of the country. Air quality. And as a consequence, that's going to be a very useful thing for us, as I'll show you in a moment, I think, with respect to plantation. All right, so basically we have a framework, and we're kind of working to develop a very simple way to make this more useful to as many people as possible. Okay, so again, things we would want to know. We'd want to know what type of crop, how much area, what are some biology principles of that particular crop, where are you located, and then how are you going to grow it. So here's some this is a complicated slide, but this is a little project we did a few years ago in working a fair bit with Portland General Electric. And what Portland General Electric was trying to do in Eastern Oregon, they're in the middle of a really amazing bioenergy transformation plan out there to essentially recycle the Boardman coal plant to a biocharcoal facility. And one of the questions is, if you're going to make a biocharcoal facility, what would the crop of choice be? And in this case, the crop of choice that they're looking at as a base crop is the grass Arundo donax. Arundo donax is particularly interesting to me because, much like poplar and some of the other plants, Arundo kind of looks like bamboo, but it's a very significant isoprene emitter. And one of the things we wanted to understand, as did Portland General Electric, to get ahead of the curve, is to make sure if you were going to incentivize the growth of this crop at a large scale, particularly in Eastern Oregon, that it wouldn't lead to unexpected problems with respect to regional air quality. And so just to kind of show you what we did, so here's a graph of a very large scale Arundo plantation. We were wondering, if you were to plant, say, upwards of 50,000 acres, and that may seem like a lot, but of course in the western states that is a doable number. If you were to plant upwards of 50,000 acres of Arundo donax in Eastern Oregon, what impact would that have on regional air quality? And what we found, and it's a little blurry, and I apologize for this, there are various dots, and I'll just cut right to the chase. The red line and the dotted red line represent various ozone standards. So that dotted red line is, the dark red line is the current ozone standard, and the dotted red line would be proposed changes to the ozone standard, which are likely to come in the next few years. What would happen? Would you get more or less ozone if you put this crop on the landscape? And what we found is that in Eastern Oregon, because the background concentrations of nitrogen oxides are so low, it's a relatively clean landscape, that that atmosphere can handle the loading associated with large-scale amounts of. And so you can see what happens. Putting Arundo on the landscape doesn't really take you over that line. But let's say Portland General Electric is successful in their model and it becomes a national standard. What would that mean if you wanted to grow Arundo donax in other parts of the country, or in fact other parts of the world? And then it gets more interesting, because then we chose different location scenarios, say Texas or Illinois. And if you look at the top, what we did is we changed basically the background atmosphere. So in Texas, this is a landscape that if you were to go down, particularly eastern Texas, you would realize, oh, there's a lot of volatile compounds in the air and there's a lot of NOx. What would happen if you load more bioenergy VOCs into that atmosphere versus, say, in Illinois, where it's a low VOC and a high NOx? What would happen there? And you can, the graph, the take-home message is kind of these panels down here, which is D and F. And basically the y-axis is the number of days, right, that you would experience various increases in ozone, right? And so literally, just by putting in a plantation here in Texas, and again, very large, but at the scale that might be interesting to the bioenergy industry, you can have increases in ozone, peak average ozone, anywhere from 1 to 6 parts per billion, from up to 5 and up to 10 days of a given year. Is that enough to be concerned about? It really very much depends on what's going on in your background atmosphere and what's going on in your Illinois, however, was interesting to me because I grew up right there on a little family farm. And Illinois is suffering from pretty high background ozone concentrations, and many of the crops that we love to grow in Illinois, Iowa, and Indiana, particularly soybeans, are particularly sensitive to ozone. So this is an area where any perturbation in ozone is something that will be taken, I think, fairly seriously. And here, with just simply putting in the plantation, what we can find is that we actually, under some scenarios, you can have actually 10, 12, in this case, 15 days where you have an increase. You can have 1 day, one to 2 days a year where you've got a 15 ppb increase in ozone simply by. So take-home message is, yes, it is a little complicated in terms of there's not a simple rule in terms of putting this crop in this landscape and what effect it's going to have in the atmosphere. You do have to know a little bit about what region you're growing in. But what was very reassuring to me is, at least here in the Pacific Northwest, and now this is again particularly for Eastern Oregon, the background air conditions are such that it really can handle the large-scale emissions that would be associated with growing that crop there. And we're continuing this type of work now throughout the Pacific Northwest, trying to really zoom down more with granularity in terms of what would be implications at what scale. But again, our current results from Oregon suggest to me we're pretty positive. All right, but how do we know what's coming out of plant leaves? And this is something we're doing. Thank you, Dennis Prant said sound is erratic. Let me try to clear that up. Maybe if I speak louder. How do we screen plants for VOC emissions? One of the things we've been working at a lot is to understand how do we profile leaf VOCs. And for any of you who have interesting crops, even beyond poplar that you're interested in screening, this is something our lab does very well. And we're really best trying to identify fingerprinting methods so that as we develop new bioenergy crops or even different cultivars of the same crop, how do we know exactly what is coming out of those leaves? And right now we probably have one of the better research groups on the West Coast to actually identify sort of plant emissions. So an area that if you're interested in analytical chemistry at any point, I'm happy to talk to you about. All right. But one thing we were surprised to discover and very happy to discover just, I guess, last summer was basically that, in the world of poplars, which we love here in the Pacific Northwest, that not all poplars are created equal. And for any of you who've been in the growing industry, you already know that's very much true. But here is an aerial image of our USDA, the AFRI Jefferson field site. So this is in Jefferson, Oregon. This is our AHB testing ground, where we have a series of genotypes of poplar put into ground in large-scale cultivation and looking at all sorts of aspects of performance and growth and physiology. So for the first time, we were screening these basically breeding genotypes for isoprene emission, and we were very surprised and happy to discover there's actually a huge range in basal isoprene flux amongst these poplar lines. Now, what that means from my perspective is it gives us great hope that, as we go forward and developing even better bioenergy poplar lines, that we now have opened up the possibility that we have enormous genomic variation, and that opens the possibility for breeding of poplar lines with reduced isoprene emission, which could be very useful in some areas, particularly if you're trying to put poplar in a more high NOx environment. So that was a very exciting thing, and we're continuing to understand the genomic basis of the variation in isoprene production in poplar, and we've also now moved into eucalyptus. But in an effort to get ahead of the curve, the other thing we've been doing in poplar, because we were wondering, because there are some parts of the world, particularly in Europe, that has a very high NOx background and would love to grow poplar, but in some areas, the consequences of air quality may be such that those regions may decide not to use that crop. So the question is, can we develop a bioenergy crop such as poplar that is a fast grower and highly productive and is good for all the various products, but doesn't have any negative consequences to the atmosphere? So what we've done is actually we've now just finished this first field trial. So we were growing genetically engineered trees that we produced here down in the Willamette Valley, and I did a lot of this work in collaboration with Steve Strauss at Oregon State and Yogi Schnitzler in Munich in Germany. And basically we identified the gene that makes the enzyme which makes isoprene, and then we turned it off. And so essentially we used some techniques, and this graph just shows these are all different, these are the same poplar trees with different amounts of isoprene production. So we figured out a way to basically tune isoprene down to the point where the tree is making no isoprene. And our question is, if we plant those under a field plantation scenario, or what impact would those have on growth, physiology, wood performance, etc. And so far, we're just deep in the weeds of analyzing that data set. It took us about 8 years to pull this project off. It was a major undertaking, and literally we just removed the plantation last spring. But long story short, these are just a few of the different genotypes. So this is a normal poplar tree. This is how much isoprene it makes. This is one of our sort of more designer poplar trees that makes no isoprene. And one thing you might want to say, well, do they grow slower, or does it have any effect? You know, we were surprised to discover, say, here's a graph of photosynthesis. There's really no impact by turning isoprene off on photosynthetic rate. Here's some more growth. This is a percent change in diameter, so this is how much the tree is growing. And essentially what we're finding is that just turning that isoprene gene off really had no effect on growth rate. So we're hopeful that in fact this is in fact a trait and a character that might be worth trying to either breed out or engineer out bioenergy crops. I'm also particularly excited to this because this is a really great example by which, genetic engineering, we're not putting any, we're not trying to make these trees glow or make them herbicide tolerant or any of the other standard uses of genetic engineering that you might hear in biotechnology. We're simply saying, can we use genetic engineering to make a tree less environmentally polluting than one that would normally be used? And that's a much different landscape to have in terms of a conversation about bioenergy and genetic engineering. So I'm looking forward to that. So stay tuned. There hopefully will be a few splashy stories about that coming up. Okay, other things that we're working on that may be of some, and that we're kind of pushing on this summer, which is really how do we make these measurements in the field. People have been making measurements of VOC emissions from field-grown plants for a very long time, and there are lots of variety of ways to do that, but oftentimes it's relatively labor-intensive. It often takes installation of large towers, or it just takes a lot of infrastructure. And I'm very interested in developing some low-cost methods that once we are perfected, that could literally be sent out to people all around the United States or even to your field. And if you really wanted to evaluate what impact VOCs are having locally, that we could help you do that. So working a lot with folks at the National Center for Atmospheric Research, we've been pushing on developing what we call a next generation system, which is called a relaxed eddy accumulation system. It's a long-winded path. Basically, it's just a fancy air sampling device. But that fancy air sampling device allows us to basically sample VOCs that are going up and VOCs that are going down over some sort of forest canopy, or it could be a grass canopy, or whatever kind of field you're interested in. And we've designed it such that you could sample and then send these cartridges that we've worked on developing back to our labs at PSU, and then we could actually tell you how much VOCs are actually either going up or in some cases going down. And I really want to emphasize the going down because what's really fascinating to me is that we probably actually know more, to be honest, about some of the negative impacts that plants, vegetation, and trees have on air quality than we do the positive. And so one of the areas that we're moving into very quickly is to do a better job understanding how certain canopies and trees might actually be leading to scrubbing or removing certain particles and pollutants from the atmosphere. So that's something that our lab is just beginning to push on, and we're going to use these sort of sampling devices to do that. The beauty of this type of approach is, it's portable, it's low cost, low power. All you need is a 12-volt battery. We can do what we call offline analysis, and then we can bring everything back to a central lab for measurement. So we're pushing on developing these little systems, particularly, clearly, bioenergy in many ways is here to stay, and we're going to see the advancement and development of all sorts of, I would say, different crops than we've seen before. We don't really understand mostly what impact those crops are having on the atmosphere, and I think we will have the tools to be able to kind of help regional land planners, farmers, growers evaluate some of these issues. Okay, so a little background to what we're up to. Again, I'm here to help answer questions as they come up, and I mostly wanted to put this presentation together because I think sometimes in the bioenergy industry, people will say, oh, but what about those VOC emissions? And I think it's important, no matter what scale you are in this landscape, to at least have a little bit of a working knowledge about this, and to be aware that this is a real issue and it's something to consider. However, it may or may not impact you depending on the scale and the nature of what you're growing. So what do we know so far? Just a little background is that this is very much a work in progress. We are working to measure and model the impacts, particularly of short rotation coppice cultivation poplar on regional air quality. We're doing this here in Oregon as well as California, and then hoping to move up farther into Washington, Idaho, if possible. And I emphasize this because one of the things that's really missing is that, as soon as it's not only what species you put in the ground or which clone you put in the ground, but it's also how do you grow it. And one of the things we've identified with our work in Arundo in Eastern Oregon is there are actually very proactive ways you can manage your crop, and perhaps through smart use of fertilizers and water regimes that can actually also lead to gains by reducing how much isoprene is produced. So there's actually a management piece as well that can be incorporated, and this is an area that we're trying to understand sort of as a general practice. What does it mean to those of you who may be interested in growing poplar, particularly in the Pacific Northwest? And to be honest, being very honest here. At this point, and I would say in most cultivation areas, especially in the Pacific Northwest, I believe it's probably relatively little. But it's important to be aware of this issue, particularly as sometimes this could be seen as yet another reason not to grow poplar, and I don't believe that at all. But it's something that we need to be aware of. But of course, if you were planting some really large-scale plantation, particularly near a very urbanized area or a high-emitting crop that we don't even know anything about yet, then this would be an important issue for you to consider. I certainly know in my work with Portland General Electric that was the case, where they had all good intention and were pushing ahead on Arundo Donax and still are, and were surprised to discover this was even an issue. And I think I was told I was their 36th major problem. But then at the end of it, after we did the science, we realized, no, this is not an issue and it's totally reasonable to move ahead. So I think that just is a smart, proactive stance in terms of getting ahead of the environmental sustainability issue and making sure that, that we aren't proposing some things that in some regions might be particularly problematic. Okay, well, with that, I just want to give some acknowledgements. I've had an awful lot of help from folks at Greenwood Resources, Brian Stanton, Jesus Espinosa, as well as the Advanced Hardwood Biofuel team, particularly Rick Gustafson up at UW for helping this project out. Mostly this work has been done an awful lot by a series of undergrads, Scott and Rose, as well as Sam, who is a RU student up from Southern Oregon. I've had one PhD student, Will Porter, who did most of the modeling, is now out at MIT, and then various help from folks at NCAR and other agencies, including Steve Strauss down at OSU. So this is an area that I hope today in this short webinar you've learned maybe a little more about than you did before. I don't want everyone to walk away thinking that trees are polluting beasts, because they absolutely aren't. However, since the very earliest days on Earth, Earth's vegetation has been shaping atmospheric chemistry, and we continue to do that today. So as we kind of march forward on sort of new cropping systems, it's just an area that I think is worth knowing about, and hopefully this webinar was helpful. Again, I am very happy to take any chat questions. I'm also happy to talk to anyone offline. Shoot me an email, and we can always also have a phone conversation if that would be of use to you. Okay, I think with that, I will go ahead and mute my mic and see if Patricia has anything for us to say. And I will also follow up on the chats here, sorry. Yes, sorry, I'm gonna follow up. So why don't I just take, if it's okay with everyone, I'm just gonna take a few chat questions. Of course, Dennis Prentice asked, have you tested the public reaction to genetic engineering for low? No, and that's a great question. I mean, that's one of the goals of this particular project is to really begin to do that. We don't, we were setting us primarily as a science research project, which is to understand, can we develop a fast-growing, competitive bioenergy crop with little impact on atmospheric chemistry, and that was our goal. But I think a consequence of what we're discovering is if it's successful, which it looks like it will be, this is going to give us the opportunity to ask, what is the public perception of this? Oftentimes in the world of, and I work an awful lot in biotech, and in the world of biotech, sometimes the public perception is generally, oh, genetic engineering just by its nature is a horrible thing. The problem is we've inherited and we're moving to a much more complicated world. And as a consequence, we're going to have to be much more smart and strategic about the research approaches and the approaches we use to deal with some really big issues. And I think bioenergy certainly is going to be ground zero for all sorts of biotechnology advances. So I'm looking forward to ways to do this. And I see Shelley Presley is typing. Shelley is a isoprene guru from the past and may have something interesting. Okay. What is the Shelley's asking, what is the resolution of our REA cartridges? By resolution, I think she's time. Thank you. That's what I thought. Yeah, so the time resolution, that's an excellent question. So the problem is not particularly high frequency. So in the way that we would collect VOCs, you can do, instantaneous online measures. So we have fancy mass specs that would allow you to act as an electronic nose, which would be high frequency. Mostly we are loading cartridges, I would say, in 20-minute total windows, something like that. So essentially we're looking at a sampling frequency of each cartridge would sample an eddy for maybe 20 minutes total loading time, but that we're doing cartridges throughout the day. So what we're trying to do is do a total diurnal time course of REA cartridges that over time will at least give us a snapshot of what's happening. Yeah. Yes, we can load more than 2 cartridges at one time. And so our goal is to develop something that we can, again, we are one, if you really are diving into the weeds of this particular topic, there are lots of amazing instruments out there that will allow you to measure VOCs and with very high frequency in real time, which I think would be the state of the science. I was looking for something that would be relatively low cost and easy and can kind of just give us a snapshot on terms of what the emissions might actually be. And Tim Volk can put your email up again, please. Yes. So actually, I will sit it here too. Loaded it up to Rosenstiel at pdx.edu, and I think, yeah. So Patricia has changed my access. So, but there is my email. And again, please, I'm happy to take any questions. I find this a very interesting area, and I think it's a great area to get people talking about sort of all sorts of connecting the dots between bioenergy, atmospheric chemistry, air pollution, ecosystems. And I will say, here in the Pacific Northwest, just as a little background, we don't have much of a history of talking about air quality in the Pacific Northwest, and that's mostly because of our history of hydropower. So if you're on the East Coast, people are much more savvy and aware of dealing with issues of air quality. And as we go to a much higher population density and larger populations, both here in the Portland and Seattle metro areas, air quality is going to be something we're going to have to begin to wrap our heads around a little more. So this is, I think, a nice area to begin that conversation. Yes. Yes, and according to Justin, yes. So Patricia is posting the presentation at hardwoodbiofuels.org, and so the references will certainly be there. And again, I'm happy to provide any other references that people may need. There aren't any other. Are there any other questions or chats? Bernie is typing. And again, if any of you, also open invitation, if any of you happen to be in Portland and would love to see what PSU is all about, please let me know. Sometimes as institutions, people forget we're even here, but we have one of the better, certainly the air groups here in Oregon. It's worth knowing about. People typing. Great. Are there comparisons to traditional, so Bernie has asked, are there comparisons to traditional cropping and native tree population? Yeah, and that's a great question. So again, there are some, and I could point you to some of those directions. I mean, what's particularly interesting about traditional cropping systems is, again, mostly these are relatively VOC-free systems. So cornfields, for example, or even sorghum. Corn and sorghum, I mean, certainly emit VOCs, but not at the scale of many of our new bioenergy crops. And so I think there's an open opportunity to really start comparing at the landscape scale what it means to put in one cropping system over the other. That said, things like switchgrass or even miscanthus or some of these other cellulosic bioenergy crops, there is a relationship between plants that tend to grow very, very fast and plants that tend to emit a lot of VOC. So even switchgrass and miscanthus, although they do not make molecules such as isoprene, some of them have been reported to release very high concentrations of sesquiterpenes. And sesquiterpenes are important because they essentially lead to aerosol particles. So I think this is a really open area. Okay. All right. Yes, and of course Brazil, there's been quite a bit of work going on in VOC production in Brazil. Luis was making a comment about that, and I'm happy to talk about that. Doing that. A few more questions. Yeah, Brazil is interesting because it is such a mixed landscape in terms of and how quickly things are changing. Um, yeah. We have published some other papers looking at, and I can send those references around, that have looked at global comparisons if we were to plant poplar over eucalyptus over switchgrass. And so we published a kind of global model comparison asking, how do you think about these issues both from a human health perspective as well as economic perspective, in terms of what is the cost of air pollution associated with planting regimes in different parts of the country. Ah, yeah, Larry Smart is asking me about the Ashworth paper. Yeah, and again, this is one of these things. So one of my intents of this presentation is, I think, following on the heels of Christie's paper and many others. I think there was this sense that, oh no, this is, as you point out, is a dire space, and that we need to super worry about it. When you look very carefully about the scale of magnitude, that the Ashworth paper was looking at. Mostly I think the bioenergy industry would say that's totally unreasonable in terms of acreage that was being considered, and in terms of total productivity. I think where Christie is correct is that, opposed to saying it's a dire aspect for this particular crop or bioenergy crop in general, is that if we're going to move in bioenergy crop direction, we just simply need to be proactive about this. And there are many options, and I presented some today showing that just simply being more careful about which clone you choose, could in many ways resolve those issues. So I don't think it's a dire prediction, but I think it certainly started to raise the flag that this is an issue that's worth considering. And again, we haven't, generally in the ag economy space, we haven't had much history of talking about how plants can manipulate atmospheric processes. I see it as a golden opportunity, and I think it's more value added in terms of really making smart, designer bioenergy crops. So. And I should say, I'm also chairing, believe it or not, there's a large group of people around the globe who think about these issues, and we have a large national conference in Girona, Spain this July, which I'm chairing, which is basically scientists, about 150 scientists from around the world who really only work in this particular area, which is how to, what we call biogenic hydrocarbons affect the atmosphere. So I'm hoping that, we'll maybe see some more examples of this. The Europeans are definitely aware of the air pollution issues as it relates to some types of cropping systems, and they're really trying to actively get ahead of that. So yeah, so I think I think although the Ashworth paper started, more of a general conversation, to me it really is more of an opportunity for us to take the breeding of bioenergy crops very seriously, much like we've done for other cropping systems. Any other questions? Don't want to hold people up today on this beautiful day, but okay. If there aren't any more, I don't see any typing questions. Happy to take again emails or phone calls offline. What I'm going to do is go ahead and mute my mic and give it back to Patricia for a little bit and see if she has any closing comments for us. Again, it was nice to chat with you all virtually today. Hopefully you learned a little bit, and I'm pleased to help. Oh, Justin is typing one more thing before I. No problem, Justin. All right, here we go. I will mute my mic and give it over to Patricia.
Good. Thank you, Todd, for a very interesting and informative webinar. Much appreciated. As I mentioned earlier, yes, this will be archived on our Hardwood Biofuels website. We have a section in there where we archive all of our webinar presentations, so we will probably be getting that up, if not tomorrow, in the very near future. This is the last webinar we're going to be having probably until September. We tend to focus on webinars during the academic year and then have our more outdoor events during the beautiful spring, summer we have here in the Pacific Northwest. So coming up on Sunday, May 15th, Jefferson, Oregon, right near where Todd is, just south of Portland. We're having a field tour at that demonstration site, which is the picture that you have on your screen here on the left side. And then at the end of May, May 31st, is our Pilchuck demonstration site that is north of Seattle and Everett. And then on June 7th, we're having a combination workshop and field tour at our site in Hayden, Idaho. So you're all invited to all of these events, and we will keep you posted on webinars coming up in probably September of this year. So if you have any questions, Todd has provided his contact information. I'm sure he's happy to follow up. And everyone have a great day. Thank you.